Hello everyone, my name is Priya and I'm an educator of Unacademy. You can follow me on Unacademy website and you can also download Unacademy learning app. So in this particular lesson we will be dealing with the MILLMA'S theorem. This is also important theorem on the topic electric circuit, right? So if you like my courses then follow me, rate and review my courses. Don't forget to give it a big thumb, and we have our YouTube channel, please subscribe it. I hope you like my lecture. Thank you.
So let me tell you regarding the lecture pattern here. So first we'll take a gate previous year question. Then we will do the related theory. So the theory required in this particular question is MILLMA'S theorem. And then we will solve the question, and by the end of the lecture I'll tell you the MILLMA'S theorem proof. So first read the question carefully. So here, viewed from the terminal A and B in the following circuit shown in a figure. This is a figure. Point A and B. So it can be reduced to equivalent circuit of a single voltage source in series with a single resistance with the following parameters, right? So basically we need to reduce this circuit into single voltage in series with a resistance. And here the options are given. So let's see how to apply the MILLMA'S theorem. Point to remember before applying a MILLMA'S theorem. It's all about the parallel configuration. You can apply the MILLMA'S theorem only on the parallel configuration. We cannot have more than one source in a branch. If you want to apply the MILLMA'S theorem, suppose it is a branch. So in this particular branch, there should be only one voltage source or one current source. There cannot be a more than one source. If there is another voltage source, then please add up according to the polarity or subtract it according to the polarity and make it a single voltage. Cannot have more than one resistance in a branch. Similarly, if there is a more than one resistance in a branch, parallel branch, then add all the resistances and make it to a single resistance. Now what is MILLMA'S theorem? It states that when a number of voltage sources V1, V2, V3 till Vn are in parallel, having internal resistances R1, R2 and Rn respectively, the arrangement can be replaced by the single equivalent voltage source in series with the equivalent resistance R. So this whole circuit we can convert it into single resistance and voltage. So how to calculate the equivalent voltage? For that we'll write here V1 multiply with the conductance G1. How to find G1? That is equals to 1 upon R1. And similarly for the second branch we'll write here V2 into G2 till the Vn into Gn conductance, right? And in denominator we'll add all the conductance, or you can here write 1 upon R1 plus 1 upon R2 till 1 upon Rn. How to find the conductance? So can you see conductance equals to 1 upon R and resistance equals to 1 upon conductance. So let's apply MILLMA'S theorem in our question. So here we have our question. We have to convert into single voltage source and a resistance. So in order to find out this equivalent voltage, first I'll write this V1 voltage multiply with the conductance. Here I'm showing the conductance with the help of Y1. So it will 1 upon R. So resistance is 6. So I'll write here 10. Multiply it 1 by 6. Moving to the second branch. First V2, that is our 5 volt. And multiply it with the conductance 1 upon resistance. And resistance is 4. So we will write here 5 by 4. And in denominator, just add up the conductance. So Y1 conductance equals to 1 upon R1. So R1 is 6 ohm, 1 upon 6 plus, here in second branch, R2 is 1 upon 4. R2 is 4, so conductance is 1 upon 4. Resistance, you know, it is 1 upon conductance. So total conductance is Y1 plus Y2. And so for that I am writing here. So you'll get a resistance value 2.4 ohm, right? So the equivalent voltage is 7 volt and resistance is 2.4 ohm. Now what is the explanation of MILLMA'S theorem? Let me tell you. So first thing you should know that Millman's theorem is given by Jacob Millman. So that is why the theorem name itself a Millman's theorem. Now, assuming that a DC network of numerous parallel voltage sources with internal resistance supplying power to the load RL as shown in the figure. Now let I represent the resultant current of all the parallel current source, and while G is the conductance of the equivalent conductance. Right? So how to find out the I? Here equivalent current, just add up all the currents, and in order to find this G, we'll add up all the G. G1, the G's are conductance here. Now next, the resulting current source, we need to convert into a voltage source. So I am using here voltage transformation, converting this current source along with the resistance into voltage source along with the resistance, right? So in order to find V voltage, what you'll write 1 upon G. See, I'm writing here 1 upon G. And you can also write here I1 plus I2 into I3, this I value, and divide it with the G. You know the G value, that conductance G1, G2, G3. Now in order to find our resistance R, 1 upon G, so 1 upon, and total conductance is G1 plus G2 plus G3. So we'll add up like this. Here the positive and negative sign appear to include the cases where the source may not be supplying a current in same direction, right? So as we know that I equals to V upon R, so in case of I, I'm writing here V upon R, now adding plus V upon R in second branch until last branch. For G, I can write conductance, I can write 1 upon resistance. So I'm replacing the conductance with the 1 upon resistance here. So 1 upon R1 plus 1 upon R2 till 1 upon Rn. Now you can replace it with again with the conductance 1 upon R value. So where the R is equivalent resistance connected to the equivalent voltage in series. So I'm replacing the 1 upon R with the G. So we'll get here V1 into G1 plus V2 into G2 plus still Vn into Gn. And in denominator, there will be a G1 plus G2 plus Gn. Or you can also directly write it in a shortcut way, that summation from k value 1 to n, Vk and Gk divided by summation from 1 to n, Gk. Or for Gk, 1 upon Rk, where k can be any value from 0 to 1. Right? So this is our final equation we'll use in Millman's theorem. Right? So this is all about our Millman's theorem. I hope you like the lecture and you know how to apply the Millman's theorem. Whenever it requires, you can easily able to identify where the Millman's theorem we can apply. So whenever you will find the parallel branches having a one source and one resistance or circuit element, you can easily apply this Millman's theorem. And these 2 points mark this point that Millman's theorem is all about the parallel configuration. It cannot have more than one source in a branch and cannot have more than one resistance in a branch. Right? So the correct answer is option B, 7 volt source in series with 2.4 ohm resistance. So friends, this is all about our today's lecture. I hope you like this lecture. Thank you. And if you like a pattern, then please comment me on the comment box so I can continue with this pattern. Thank you.